So a very good evening everyone. Just quickly confirm audio video is clear. Kindly confirm audio video is clear, everything is good. Kindly confirm the audio video, is it clear? Just one confirmation and then we can start the session. Clear? Okay. So a very good evening everyone. Welcome to this session of quick revision of strength of material. In today's session, we will going to specially focus on those areas, Namaste Manav. We will going to focus on those areas for which the chances of getting asked in the examination will be highest. Okay. And we will be taking some of the PYQs which will help you to revise the content in very less time. Although we will going to cover all the chapters, I will going to write down all the formulas. So this is the time that you should also prepare your formula sheet if you haven't prepared till now. Okay. So this is our session. Let me start with the first thing, my dear. If we talk about the flow of this subject of strength of material, it starts from simple stresses and strain, then shear force and bending moment diagram, then bending and shear stresses in beams, then torsion of shaft comes. After that you have principal stresses and strains, then you have deflection of beams, then thin pressure vessels, and then the last one be columns analogy, that is the total subject. Now starting from the first chapter, simple stresses and strain, first thing is stress. So stress is basically the internal resisting force divided by area. Stress is the internal resisting force divided by area. Now sir, depending upon the type of area you are considering, these stresses are of two types. First one is called as engineering stress. So engineering stress is termed as the internal resisting force divided by the original area A0. And then you have the true stress. True stress is equal to the internal resisting force divided by the actual area. Please take care of both the things. Okay. In the examination, if they are asking, sir, test mein 30 marks aa rahe hain, bas, it will going to improve. Rajat, don't worry. We have to give more number of tests. So stress is the internal resisting force per unit area. Based on the type of area you are taking, stresses are of two types, engineering stress and true stress, right? And Rajat, one more thing, if you belong to mechanical engineering, definitely this session will going to improve 4-5 marks in your examination. Then after this we have strain. So strain is termed as the change in length per unit length. Strain is change in length. Strain is change in length per unit length. Again, based on the type of length you are considering, these strains are of two types. First one is called as the engineering strain. So engineering strain is equal to the change in length per unit original length. Change in length per unit original length is your engineering strain. And then you have the true strain. So true strain is equal to, true strain or actual strain is equal to the change in length per unit the actual length. There is one more expression for true strain or actual strain, which is equal to integration of dl by L, and this limits are from L0 to LA. That gives you one more expression for actual strain, which is natural log of LA by L0. While I am writing all the formulas, you also keep on writing with me, right? Don't sit and relax. Just keep on working with me so that even you can prepare this formula sheet in very less time. So this is another expression for your actual strain. There is one relation between actual strain and your engineering strain. So actual strain is equal to natural log of 1 plus your engineering strain, right? Epsilon naught is your engineering strain and epsilon A is your actual strain. After this, sir, there is one relation between engineering stress and true stress. So engineering stress, so true stress or actual stress is equal to, actual stress is equal to your engineering stress into 1 plus minus engineering strain. So these are very important relations from the first part of the story of strength of material, where we talk about stresses and strain. Stress is measured in megapascal or Newton per mm square, whereas strain is a unitless quantity. After this, my dear, since we talk about homogeneous and isotropic material, homogeneous material means the property of the material is same along a particular direction. But when we talk about isotropic material means the property of the material at a point is same in all the directions. When you combine homogeneous and isotropic material together, it means that the property of the material is same at all the points in all the directions. Based on that, we have the Hooke's law. Now sir, there are three Hooke's laws. First one is Hooke's law for axial loading. Hooke's law for axial loading states that stress is directly proportional to strain, and removing this proportionality sign, you will get the first expression that stress is equals to E into strain, right? This is the first Hooke's law for your axial loading. The second Hooke's law for shear loading states that the shear stress is directly proportional to shear strain. Removing the proportionality sign, shear stress is equal to G into phi, where G is called as the modulus of rigidity. Third one is the shear stress for hydrostatic loading, which states that the change in pressure minus delta P is directly proportional to your volumetric strain. Removing this proportionality sign, you will get the expression that minus delta P is equal to K into epsilon V, right? So you have 1, 2 and 3 Hooke's law, and for that Hooke's law you have 3 elastic constants. E, G and K are 3 elastic constants. After that, the fourth elastic constant mu is equal to minus of lateral strain to longitudinal strain, minus of lateral strain to longitudinal strain, minus of lateral strain to longitudinal strain, right? So we have basically 4 elastic constants here. E, G, K and mu are 4 elastic constants. Then sir, after writing all these expressions, we know that these elastic constants are also related with each other by a certain set of formulas. Now for the relation between elastic constant, the first relation is E is equals to 2K into 1 minus 3 mu. Sorry, E is equals to 3K into 1 minus 2 mu. This is the first relation. Second is E is equals to 2G into 1 plus mu. E is equals to 2G into 1 plus mu. Third one is E is equals to 9 kg. E is equals to 9 kg upon 3K plus G. And fourth one is mu is equals to 3K minus 2G, 3K minus 2G upon 6K plus 2G, upon 6K plus 2G. So these are the 4 important relations between the elastic constants. Now sir, if my material is isotropic and homogeneous, for isotropic material, you require 2 constants. If you remember or if you know the value of any 2 elastic constants, you can find out the value of any of the elastic constants which are listed here, right? Similarly, for orthotropic material, there are 6 independent elastic constants, and for non-isotropic material, there are 21 independent elastic constants. So that also you should remember. Okay, so after this, after having all these elastic constants, can you just quickly solve this numerical? I will write the question here, for which E is equal to 200 gigapascal and mu is equals to 0.3. Can you find me the other 2 elastic constants? I will just give you 2 minutes of time. Please quickly tell me the value. Please quickly tell me the value of other 2 elastic constants. I will give you 2 minutes of time. We have to revise the entire content. So stay with me till the end. And whenever I am asking you, just quickly do the calculation. Apply the formula and do the calculation. Be quick. Do it quickly. And keep commenting your answers. All of you keep commenting your answers. Keep commenting your answers. Sir, formula orthotropic we have 9 and elastic constants. Yes, beta, for orthotropic there are 9 independent elastic constants, and for non-isotropic we have 21 independent elastic constants. I'll write here isotropic, two independent elastic constants, orthotropic 9, and then non-isotropic 21. Go for it. Very good, Manav. Very good. K is 111.11. Go for mu G also. Keep commenting your answers. Do it quickly. All of you keep commenting your answers. Whatever answer you are getting, keep commenting. Okay, so E and mu are given to you. I need to find out the value of K and G. So I have the first relation E is equals to 3K into 1 minus 2 mu. So E is equals to 200. This is equals to 3 into K into 1 minus 2 into 0.3. Please do the calculation quickly. Even I have the calculator today. Yeah, Chinmay is saying G is 76.92. Okay, what is the value of K? Let me just quickly confirm this. So this is 200 divided by 1 minus 0.6 divided by 3. Why I am getting 166.67 K gigapascal? The value of K is 166.67. 111, beta, check it, check your answer again. This is 200, 3K into 1 minus 2 mu. So 1 minus 0.6 will be 0.4. 200 by 0.4. Yeah, so this is 166.67. Now the next relation we have is E is equals to 2G into 1 plus mu. So E is equals to 200 is equal to 2G into 1 plus 0.3. Do this. So this will be 100 by 1.3. So 76.92 is the correct answer here. G is equals to 76.92 gigapascal. 76.92 gigapascal. Go for it. Right. So this is the value of G and K. Like this you can go for. Try this question quickly. Just 1 minute of time for you. Everyone quickly reply on this. 1 minute of time for you. Go for it. Go for it. Go for it. Go for it. We have to solve a lot of questions today, so quickly do it. Answers, please. What are your answers you are getting here? So the question is saying for a material having modulus of rigidity G as 100 gigapascal. So the value of G is 100 gigapascal. G is 100 gigapascal. And the Poisson's ratio of 0.25, mu is equals to 0.25. You need to find out the value of Young's modulus and the bulk modulus. So first I will use this relation E is equals to 2G into 1 plus mu. E is equals to 2G into 1 plus mu. Therefore, E is equals to 2 into 100 into 1 plus 0.25. So what is 200 into 1.25? Quickly. 2 into 1.25, 200 into 1.25 will be 250. Very good. So E is coming out as 250 gigapascal. Now get me the value of mu. Get me the value, sorry, you have to calculate the value of bulk modulus. So for bulk modulus, you can go with this. E is equals to 3K into 1 minus 2 mu. So E, you already calculated 250 gigapascal. This is equals to 3 into k into 1 minus 2 into 0.25. Get me the value of k quickly. Please tell me the value of k. Everyone, please tell me what will be the value of k. How much is k? Please tell me the value of k. What is the value of k here? So this is 250 divided by 0.5 divided by 3. So this is again 166.67. All of you just quickly confirm, are you getting the same answer or any other answer? Yeah, so k is 166.67, absolutely correct, right? So one of the basic area from where you can expect a easy 1 mark question, okay? Before moving ahead, I have to make few of the announcements. First one is, we at IMS Gate Academy, we are providing you with India's largest test series, and now this is offered to you at a discounted price of 40%, where we are providing you with 130 plus tests starting from the chapter test, subject test, multiple subject test, advanced subject test, and the full length mock test. We are also providing you with the 33 years of GATE question bank of maths aptitude and your technical subject, which contains the detailed solution, alternate solution, key points, and chapter overview, along with the video solution. We at IMS Gate Academy, my dear, we offer you 4 different types of courses where 800 hours of live teaching with interaction is provided. Along with that, we provide you with theory and exercise book containing 4,000 practice questions, well versed in level 1, level 2 and level 3, so that even you have a proper idea in which level is your preparation. We provide you with 34 years of GATE question bank along with 12 personalized one-to-one mentoring sessions, so that your preparation is well oriented, motivated, guided and targeted preparation you can have. Along with that, we provide you with India's largest test series containing 130 plus tests. If you want to know more about our courses, you can book a free online counseling session, for which the link is provided to you in the description box. We also have a zero fee program where we are providing you with 50 hours of concept videos along with 3 GATE chapter and subject test, 1 personalized guidance session and GATE 24 paper with solution, my dear. So if you want to check our product, how we do at IMS Gate Academy, again for this zero fee program, the link is provided to you in the description box. Let's move ahead with this, my dear. So these are the basic announcements I have. Now after this, if I have to tell you something about a material, for example, this is a body which is subjected to stresses like this. This is a body which is subjected to triaxial loading, which is sigma x like this, sigma x like this, then you have sigma y acting like this, sigma y acting like this, then you have sigma z acting like this. This is sigma z here, okay? This is sigma z, okay? Now, for example, for this type of loading, this sometimes asks you what is the strain along x, y or z direction. In any direction, they can ask you the strain, and they can even ask you the volumetric strain. So, for example, for this complex state of, for this 3D loading, for this triaxial loading, which is subjected to a normal stress of sigma x, sigma y and sigma z, what can be the value of strain in x direction? So, strain in x direction is equal to sigma x by E. Strain in x direction is sigma x by E. Sigma x is trying to increase the length, but the Poisson's effect of sigma y and sigma z is trying to decrease this length. So I will write down the Poisson's effect of sigma y will be mu times of sigma y upon E minus mu times of sigma z upon E, right? So I started from sigma x, then I have taken the Poisson's effect of sigma y and sigma z on this length. Similarly, if I have to write down strain along this y direction, so strain along y direction, epsilon y is equal to sigma y by E. Now check the Poisson's effect. The Poisson's effect of sigma x and sigma z will try to reduce the height of this element. So I will write down minus mu times of sigma x by E minus mu times of sigma z by E. Okay. Similarly, the strain in z direction, epsilon z, is equal to sigma z by E minus mu times of sigma x by E minus mu times of sigma y by E. if you have to calculate the volumetric strain, so volumetric strain is simply the sum of strain in x direction plus strain in y direction plus strain in z direction. So the value of volumetric strain from here will come out as volumetric strain epsilon V is equal to sigma x plus sigma y plus sigma z divided by E upon 1 minus 2 mu. Divided by E into 1 minus 2 mu. This is the value of your volumetric strain for this 3D state of loading, right? So if any state of loading is given to you, using these formulas, you can find out the value of strain and the volumetric strain along any particular direction. After this, sir, we have something called as differential form of strains. Differential form of strains. Differential form of strains. Differential form of strains. I am just writing the formulas, all the explanation, everything we have seen in the class in detail. So for example, if U, V and W are the change in x, y, z coordinate, are the change in x, y and z coordinate, x, y and z coordinate due to external loads, then what can you say about the normal strain in x direction? So normal strain in x direction is equal to del u by del x. Similarly, normal strain in y direction, epsilon yy, is equals to del v upon del y. Similarly, normal strain in z direction is equal to del w upon del z. So these are the values of your normal strain along x, y and z direction, and these are termed as the differential form of strains. So these are your normal strains. I'll write here. These are your normal strains. These are your normal strains along x, y and z direction. Similarly, if you have to write down the shear strains, differential form of shear strains are like this. The differential form of shear strains are like this. If you want to write down shear strain phi xy, the differential form of phi xy is del u upon del y plus del v upon del w. Del u upon del y plus del v upon del x, right? You have to just interchange. This is the change in x, therefore it has to be partially differentiated with y. Like that we used to remember, okay? Then you have phi xz. So phi xz is equals to del u upon del z plus del w upon del x. And last one is shear strain phi yz is equal to del v upon del z plus del w upon del y. So these are the differential forms of your shear strains. Whenever any change is given to you in x, y and z direction, this is how you need to write down the value of normal strain and the shear strain, okay? After this, we have the properties of the material. In that, quickly, let's see the stress strain curve for mild steel. So this is the stress strain curve for mild steel. Quickly, everyone. This is the stress strain curve for mild steel. Few important things we will going to see here. So stress strain curve for mild steel. First of all, sir, y stress is plotted on the y-axis. Anyone? Y stress is plotted on the y-axis. Anyone? Quick answers. Y stress is plotted on the y-axis and strain is plotted on the x-axis. Y stress is plotted on the y-axis and strain is plotted on the x-axis. Quick answers, please. Y stress is plotted on the x-axis and strain is plotted on the y-axis and strain is plotted on the x-axis. Quick answers, please. Anyone? Anyone? Quick answers. Y stress is here and strain is here. Y stress is here and strain is here. Quickly, everyone. Sir, stress is a function of strain. Fantastic answer, Manav. Fantastic answer. My dear, when you apply the load, due to this load, the body will undergo deformation. In order to resist the deformation, stresses are induced. So first, on the application of load, the body will undergo deformation, means strain will come. In order to resist that strain, stresses are induced. So always remember that stress will be the function of strain. Stress is the function of strain. So which one is the dependent parameter? Your stress is the dependent parameter on strain, and strain is the independent parameter. Very good answer, Manav, very good. So that is why your stress is plotted on this independent axis and strain is plotted on this dependent axis. When you draw the stress strain curve for mild steel, it starts like this. It starts like this. Okay, so first of all, you will get the proportionality limit A. So from O to A, your Hooke's law is valid and A is termed as the proportionality limit. After A, the curve will be non-linear and you will get the elastic limit B, right sir? So O to A, the curve is linear, Hooke's law is valid, and the very important thing is the slope of line OA is termed as the Young's modulus. Then from A to B, the curve will be non-linear, okay? Till B, whatever strain that will come over the body, that strain is termed as the elastic strain. So till B, whatever strains are coming over the body, these value of strains are called as elastic strains. These are termed as elastic strains. On the removal of load, these elastic strains can be regained, right? On the removal of load, the material can regain the elastic strain. After this, plastic deformation starts beyond point B. On loading the material, plastic deformation starts and you will get the upper yield point C dash and the lower yield point C, right? This fall in stress from C dash to C takes place at constant value of strain, and this fall in stress from C dash to C is because of the slippage of carbon atom inside the internal structure of mild steel. So at C, at constant value of stress, we see huge deformation which is termed as yielding. The stress corresponding to which yielding deformation takes place is called as the yield stress, which is also termed as the yield strength of the material. So at this constant value of stress, you will see huge deformation, and this CD is termed as the yield plateau. CD is termed as the yield plateau, TEAU. It is termed as the yield plateau. Now during yielding, what will be happening inside the structure? During yielding, the reorientation of the internal structure of mild steel takes place, and at this point D, you get a brand new configuration of mild steel which is capable to resist more amount of load on the application of load. Then you can see this beyond point D, on loading the material you will get the strain hardening zone, and you have the ultimate load point which is also called as the ultimate tensile strength of mild steel. So this DE is called as the strain hardening zone. This is called as strain hardening zone. Why strain hardening? Because in this portion additional resistance is offered by the mild steel. So this is called as strain hardening zone. This is termed as strain hardening zone. This is termed as strain hardening zone, and this E is called as the ultimate load point. The stress corresponding to point E is called as ultimate tensile strength. The stress corresponding to E is called as ultimate tensile strength, UTS. After that, the necking starts, the reduction in the cross-sectional area, and you will get the fracture of the material at point F. Okay, sir. So this EF is called as the necking zone. This EF is called as the necking zone, right? The total strain corresponding to point F is called as the fracture strain. The total strain corresponding to point F, this strain corresponding to point F is called as the fracture strain. Now very important thing here, till point B you are having elastic strain. Beyond point B, whatever strain will be coming in the material, it is termed as plastic strain or non-elastic strain or post-elastic strain. Any of such word is written in the examination in the question, you should be aware about this. So this value of strain is called as plastic strain. This is called as plastic strain. This strain is also called as post-elastic strain. Post-elastic strain, post-elastic strain, and clearly you can see the difference between post-elastic strain and the fracture strain. Fracture strain is the total strain from here to here, total strain till fracture is called as fracture strain. But beyond point B, whatever strain will be coming, it is termed as plastic strain. Based on this property, we have defined one fantastic property of the material which is termed as ductility. A material is said to be ductile if this plastic strain is more than 5%. Quickly, so what is ductility? If plastic strain is more than 5%, then the material is said to be ductile. If this plastic strain is less than 5%, if plastic strain is less than 5%, then the material is said to be brittle. So if you have to compare between two materials, which material is ductile, which material is brittle, you have to observe the plastic strain. Whichever material has highest value of plastic strain, that material will be more ductile. Now next thing is, the next property of the material is termed as elasticity. Now sir, how to measure elasticity? The way of measuring elasticity of any material is simply measuring the slope of the initial portion of stress strain curve. Indirectly what I mean to say is, just see the value of Young's modulus. The material having highest value of Young's modulus will be highly elastic. The material having less value of Young's modulus will be less elastic. So sometimes while teaching I give you this example that out of steel and rubber, which one is more elastic? So our mind starts thinking in this direction, ki sir, in rubber if I apply the load it will going to elongate easily. No my dear, that is not elasticity. Elasticity is measured by the value of Young's modulus. Whichever material has highest value of Young's modulus, that will be highly elastic. So I'll just write here, material having high value of Young's modulus will be more elastic. Material with more value of Young's modulus will be more elastic. Material with more value of Young's modulus will be more elastic. Let me just quickly write this. Material with more value of Young's modulus will be more elastic. Material with more Young's modulus, more elastic. More Young's modulus means more elastic, Now next is toughness, resilience. So resilience is the strain energy stored in the body up till the elastic limit. Resilience is calculated by area under load deformation curve. Then second one is the modulus of resilience. Modulus of resilience is the strain energy stored in the body per unit volume up to the elastic limit, and the modulus of resilience is calculated as sigma y square divided by 2e. This is your modulus of resilience. Then comes the toughness. So the total strain energy stored in the material till the fracture point is termed as toughness, again calculated by area under load deformation curve. Then you have modulus of toughness. So modulus of toughness is basically strain energy stored per unit volume till the fracture point is termed as modulus of toughness. For calculating modulus of toughness, you need to find out the total area of the stress strain curve. Now one more thing, which materials will be more tough? Material which has higher area under stress strain curve will be more tough. Now in order to decide which material will have higher area, again observe this plastic strain. So it has been observed that ductile materials are having more area under stress strain curve than the brittle materials. Therefore, ductile materials are more tough than the brittle material. So I will write down ductile materials are tougher than brittle materials. Ductile materials are tougher than brittle materials. Ductile materials are tougher than brittle materials. So these are the important thing about the properties of the material. Okay, let's move ahead with this. After this we see the elongation, the axial deformation of the prismatic bar. For example, if this is a bar which is subjected to an axial load of P, the length of the bar is L, area of cross section is A, and the Young's modulus of the material is E. Then first of all, the stress developed in the bar, we are talking about engineering stress, right? A stress developed in this prismatic bar is equal to P upon A. Next, strain in this bar is equal to change in length per unit length of the bar. So this is your stress, this is your strain, right? If you have to observe the deformed shape, this is how the deformed shape will look like. For this bar. So initially it was L, after deformation it became L dash. So delta L is nothing but L dash minus L, right? So from here, when you know the stress, when you know the strain, sometimes they ask you what is the deformation delta. So for calculating that, you can use the Hooke's law. So by Hooke's law, I can write down, stress is equal to E into strain. What is stress? Stress is P upon A is equal to E into strain is how much? Strain is delta L upon L. So from here you can calculate the value of delta L, which is coming out as PL upon AE. So delta L is equals to PL upon AE. Now here there is one very important term which is called as AE. AE is called as axial rigidity. AE is termed as axial rigidity. Can anybody tell me what is this axial rigidity? What does this axial rigidity explains me? What is axial rigidity AE? Anyone quickly, what is this axial rigidity AE? What is axial rigidity AE? Quickly, anyone? What is axial rigidity AE? Anyone? What do you mean by this axial rigidity AE? What is the physical significance of this? So axial rigidity AE simply tells us about the resistance offered by the material against axial loading. More axial rigidity means more resistance will be offered by the material against axial loading. Means, for example, if there are two materials given to you, say this is material 1 and this is material 2, right? Both are, this is material 1 and this is material 2, both of them having the same length, same cross-sectional area, but Young's modulus of material 1 is more than the Young's modulus of material 2, right? E1 is more than E2. Young's modulus of material 1 is more than the Young's modulus of material 2. Now, if the same amount of load is applied over both the materials, can you tell me which material will undergo more deformation? Which material undergoes more deformation? Material 1 or material 2? Very good, Manav. Very good, Chinmay. I'm asking which material will undergo more deformation. If I have given you that length area of material 1 is same as that of material 2, but Young's modulus of material 1 is more than Young's modulus of material 2. On the application of same load over both the material, on the application of same axial load over both the material, which material will undergo more deformation? Material 1 or material 2? Quickly. Which material will undergo more deformation? Material 1 or material 2? Material 2 will undergo more deformation than material 1. Fantastic answer. And how have you made this? Because axial rigidity of material 1 is more than axial rigidity of material 2, due to which material 1 will offer more resistance than material 2. Hence, material 2 is easy to deform compared to material 1. So, material 2 will undergo more deformation. So, material 2 will undergo more deformation. Material 2 will undergo more deformation. Material 2 will undergo more deformation. Will undergo more deformation. More deformation. Okay. Now, sometimes either you will use this axial rigidity, or there is one more parameter which is termed as axial stiffness. AE by L is termed as axial stiffness. AE by L is termed as axial stiffness. Now, sir, axial stiffness also tells you about the resistance against axial load, but axial stiffness tells you in per unit length. How much amount of resistance is offered by the material per unit length against the axial deformation is explained by your axial stiffness. Both of them meaning the same thing, but axial stiffness is per unit length and axial rigidity is about the total length. Okay, sir. Now, after this, these prismatic bars can be connected in series and parallel. Let's see connection of prismatic bars. Connection of prismatic bars. Connection of prismatic bars. So, if the prismatic bars are connected in series like this, for example, these are the prismatic bars which are connected in series. These are the prismatic bars which are connected in series. Quickly. These are your prismatic bars which are connected in series. So, what will be the common thing among all the prismatic bars? These are the prismatic bars connected in series. And the assembly is subjected to an axial load of P. The area of cross section for material 1 is A1, E1, L1, A2, E2, L2, and then you have A3, E3, L3. So what is the common thing among all the materials? Anyone? So when these bars are connected in series, first of all, load in all the materials will be same. P1 is equals to P2 is equal to P3 is equal to P. So when these bars are connected in series, load in all the individual components will be same. But the total deformation delta is the sum of individual deformation, delta 1 plus delta 2 plus delta 3. So whenever the bars are connected in series, all the components will be subjected to same load, but they will be subjected to different deformations. Fantastic answer, Chinmaya. Very good. So delta is equals to P1 L1 upon A1 E1 plus delta 2 is equals to P2 L2 upon A2 E2 plus delta 3 is equals to P3 L3 upon A3 E3. Now I know that P1 is equals to P2 is equals to P3, so I have to simply write down delta is equal to P inside bracket you have L1 upon A1 E1 plus L2 upon A2 E2 plus L3 upon A3 E3. Okay, so these are the bars connected in series. Similarly, you have the bars connected in parallel. Second one is for the bars connected in parallel. For example, there are 3 prismatic bars connected in parallel. These are 3 prismatic bars which are connected in parallel like this. Bar number 1, 2, and say 3. So this is A1, E1. Length of all the bars is same, A2, E2. And then you have A3, E3. And this assembly is subjected to a load, a total load of P. This assembly is subjected to a total load of P. So when the bars will be connected in parallel, what will be one common thing among all these bars? Anyone? When these bars will be connected in parallel, what will be the thing common among all these bars? Anyone? What will be the common thing among all these 3 bars? Everyone, just quickly reply on this. When these bars will be connected in parallel, the common thing among all these bars will be deformation delta. So deformation delta, so delta 1 is equals to delta 2 is equals to delta 3 is equal to delta. Now the important thing is this total load P will be distributed among all the 3 bars like this. This total load P will be distributed among all the 3 bars like this. This is P1, then this is P2, this is P2 here, and then this is P3. The total load P will be distributed among all the 3 bars. So I would like to tell you that P is equals to P1 plus P2 plus P3. And in order to find out the value of this P1, P2 and P3, we will going to use the formula directly. So P1 is equals to the weighted average of P. So P into A1 E1 divided by sum of AE. Like for all the members, you have to take the sum of A1 E1 plus A2 E2 plus A3 E3. That is the value of P1. Similarly, the value of P2 is equal to P into A2 E2 divided by the sum of all the axial rigidity AE. Similarly, you can calculate P3. P3 is equals to P into A3 E3 divided by the sum of all the axial rigidity AE, right? So like this, you should remember how to deal with the series in the parallel connection. After this, sir, after calculating the deformation or the axial deformation of the prismatic bars, we have the tapered bars. So let's see the formulas also. For example, if you have the circular tapered bar, so deformation of the tapered bars. Deformation of the tapered bars. Deformation of the tapered bars. Now, sir, what is the deformation for tapered bar? First of all, if you have the circular tapered bar, first one for the circular tapered bar, whose diameter is increasing, the total deformation delta is equals to 4PL upon pi E d1 d2. This is the total deformation of the circular tapered bar. Next, for rectangular tapered bar, whose width is increasing from B1 to B2, at constant thickness T, so total deformation delta is equals to PL upon TE log of B2 by B1 upon B2 minus B1. PL upon TE log of B2 by B1 upon B2 minus B1. So this is the deformation of the circular and the rectangular tapered bar. Please remember this. Now next one is, if you have a bar which is subjected to self-weight. So deformation of the bar subjected to self-weight will be deformation of the bar subjected to self-weight. So deformation of the bar under self-weight is deformation of bar under self-weight. Deformation of bar under self-weight is calculated like this. Deformation of bar under self-weight. For example, if this is a bar which is subjected to self-weight, the unit weight of the bar is gamma. The unit weight of this bar is gamma, then the total deformation under self-weight. So gamma is the unit weight. So under unit weight of gamma, the total deformation delta is equal to gamma L square upon 2E. Total deformation delta is equals to gamma L square upon 2E. This is the deformation under self-weight. Anywhere you can see the cross-sectional area. So one very important thing is, your deformation under self-weight is directly proportional to the square of the length. It is inversely proportional to the Young's modulus, and it is directly proportional to the unit weight, but it does not depend on the cross-sectional area. So I will write down delta under self-weight. Delta due to self-weight does not depends on area. Does not depends upon area. Does not depends upon area. It does not depends upon the area, right? So this is the deformation under self-weight. Okay, sir. So after finishing this much amount of the topic, let's see some of the questions here. I have kept few questions. This is the first question. I'll give you 1 minute of time. Go for it and solve this. Just 1 minute of time. It's a very easy question for you. Solve this. Question is visible to everyone? Question is visible to everyone? Solve it, solve it. Solve it, get me the answer. So the question is saying, in a material under a state of plane strain, a 10 by 10 mm square centered at a point gets deformed as shown in the figure. So you have this plane lamina which is subjected to shear stresses, and due to that shear stresses, you got this kind of deformation, right? So this internal angle between the plane here will be 90 plus phi xy. Very good. If they are saying this is equal to pi by 2 plus 0.0005 radians, and if the shear strain phi xy at this point is expressed as 0.001 K, then the value of K is. So first of all, this total angle here is either 90 plus phi xy, or it is also equal to pi by 2 plus this value. So you can use any of the values. So if you are going with radians, I will go with this. So I will say pi by 2 plus 0.0005 is equal to, this total angle here will be pi by 2 plus phi xy. This is pi by 2 plus phi xy. This is the shear strain phi xy, and the value of shear strain is given to you. So this pi by 2 and pi by 2 will cancel out, right? You can substitute the value of phi xy. So phi xy is equal to 0.0005. So phi xy is given to you as 0.001 k, 0.001 k, that is equal to 0.0005. So from here the value of k will come out as 0.5. The value of k will come out as 0.5, right? So like this you need to solve this question. It's a very simple question. Why I have taken this question? Because of this internal angle. For example, if the shear strains or shear stresses are acting, let me see this quickly also. If this is my plane lamina, and over this plane lamina, if the shear stresses are acting like this, this is tau xy, this is tau yx, then this is tau xy, again this is tau yx, this is tau xy, this is tau yx, again this is tau xy, this is tau yx. So due to this, the plane lamina will going to deform like this. And this is equal to phi xy by 2, and this is also equal to phi xy by 2. Now if these two are phi xy by 2, then this angle beta is equal to, beta will be 90 minus phi xy by 2 minus phi xy by 2, 90 minus phi xy by 2. So beta will be equal to 90 minus phi xy. So when these type of deformation comes, this is how you need to write down. Okay, beta is equals to 90 minus phi xy. For the other case, we have already seen that the internal angle will be equal to 90 plus phi xy. Now after this, one more small thing is stress tensor. So when we write down stress tensor, it is like this. Stress tensor is sigma xx plus tau xy plus tau yxz. Then you have tau yx, sigma yy, and then you have tau yz. And then you have tau zx, tau zy, and then you have sigma zz, right? So this is your stress tensor. Now in this stress tensor, if you replace normal stress with normal strain, replace sigma with epsilon, and replace shear stress with shear strain by 2, you will get the strain tensor. So strain tensor will be you have epsilon xx, then you have phi xy by 2, then you have phi xz by 2, then you have phi yx by 2, then you have epsilon yy, then you have phi yz by 2, and then you have phi zx by 2, phi zy by 2, and then you have epsilon zz. Now in both these tensors, stress and strain tensors, both of them are square symmetric matrix. Both of these tensors are square symmetric matrix. They are square symmetric matrix. Square symmetric matrix. And when I am saying square symmetric matrix, then I can write down, for square symmetric matrix, I can write down that tau xy is equal to tau yx, tau xz is equal to tau zx, tau yz is equal to tau zy. Okay. And these are termed as complementary shear stresses. These values are termed as complementary shear stresses. The same thing I can write down for strain, that is phi xy. Phi xy will be equal to phi yx. Phi yz is equal to phi zy. And then you have phi xz is equal to phi zx. Okay. So this is how you need to deal with the stress and the strain tensor. Okay, let's move ahead with this. We have another question. Try this question. Just 1 minute of time for you. Go for it. Read the question and tell me the answer for this. It's a very easy question. Take 2 minutes. Go for it. Solve and get me the answer. Solve it and get me the answer quickly, everyone. Solve it. Go for it. Please tell me the answer for this. Very good, Manav. All of you just quickly reply on this. Correct answer, Manav. Absolutely correct. So question says that a plate in equilibrium is subjected to uniform stresses along its edges with magnitude of sigma x is 30 megapascal, sigma y is 50 megapascal. This is 30, this is 50, and there is no stress acting in the z direction. The Young's modulus of the material is 2 into 10 raised to power 11 Newton per meter square and the Poisson's ratio is 0.3. If sigma zz is negligibly small and assumed to be 0, sigma zz is 0, then the strain epsilon zz is. So let me just quickly draw this state of stress. So this is your state of stress here. Sigma x and sigma y are acting, only sigma x and sigma y are acting like this. So this is sigma x here, this is sigma x, then you have sigma y, this is sigma y here, sigma x, sigma y, again sigma x and sigma y. Right, so sigma x is given to you as 30 megapascal and sigma y is given to you as 50 megapascal. Young's modulus is 2 into 10 raised to power 11 Newton per meter square. Check this out. I can write down this as 2 into 10 raised to power 5 megapascal. Right. 2 into 10 raised to power 5 megapascal. Now next is Poisson's ratio is given to you as 0.3. So mu is given to you as 0.3. Check this out. So strain in z direction, epsilon z is equal to sigma z by E minus mu times of sigma x by E minus mu times of sigma y by E. Right. So sigma z is equal to 0. So this first term will be 0 here. You have epsilon z is equal to minus mu by E of sigma x plus sigma y. Substitute the value, get the answer. 1 minute question it was. So epsilon z is equal to minus 0.3 divided by 2 into 10 raised to power 5 megapascal into 30 plus 50. 30 plus 50. So this will be 80. So I think this will come out as epsilon z is come out as minus 120 into 10 raised to power minus 6. All of you just confirm this. Is it coming out as minus 120 into 10 raised to power minus 6? Kindly confirm this answer. So 0.3 into 80 divided by 2. Yeah, so this will be 120 into 10 raised power minus 6. This is your epsilon z. So let's move ahead with this quickly. So this is your epsilon z. Let's move ahead with this. Try this question. So this is a good question. Try it, right? It's a question from thermal stresses. Two minutes of time again. Go for it. Go for it. Go for it. Go for it. It's a 1 mark question, remember. Go for it. Kindly solve this question. Please solve this question. It's an easy one. Go for it. It's a very easy question. Go for it. Okay. So the question is saying that a elastic bar of length L, uniform cross-sectional area A, and coefficient of thermal stress, thermal expansion alpha, and Young's modulus E is fixed at the two ends. The temperature of the bar is increased by T degrees Celsius, resulting in the axial stress of sigma. Now this axial stress we already know. It is termed as the thermal stress. Okay, sir. Keeping all other parameters unchanged, if the length of the bar is doubled, then the axial stress would be. It's a very easy question. Check this out. For example, this is your bar, and this bar is fixed or restricted at both the ends like this. This bar is restricted at both the ends like this, right? This is the bar of length L restricted at both the ends like this. The length of the bar is L, area of cross section is A, Young's modulus is E, right? Now, if the temperature is increased by T degrees Celsius, I will write down, if the temperature is increased by T degrees Celsius, or usually we have a habit of delta T, but let me take T here. If the temperature of the bar is increased by T degrees Celsius, then how to calculate the thermal stresses? We know that because of this restriction, thermal stresses sigma will be developed here like this. Due to the restriction, the bar wants to expand, but due to this restriction, the thermal stresses will be induced here. For calculating the thermal stress sigma in this x direction, I will write down delta net along x is equals to 0. So I will write down delta net along x is equal to 0. So delta net along x is free expansion minus effect of sigma, right? So if there would have been no support, this bar would have been easily deformed like this, and this deformation is termed as the free expansion. This portion of the deformation is termed as the free expansion, but support is present, so this free expansion is not allowed, and due to which sigma will be produced here. Now see the free expansion. So this total should be equal to 0. Free expansion is equals to L alpha delta T, which is T degree Celsius, minus sigma by E into L equal to 0. So from here the value of sigma is coming out as E alpha T. So this is the value of sigma. From here only I can conclude that with change in length, there will be no impact on the thermal stress. Even due to change in length, there will be no impact because thermal stress is not depending on the length. But again, if you want to prove it, this is how we can go for. So this is a new bar which is having the total length of 2L. This is a new bar which is having the total length of 2L. The total length here is 2L. Area is A, Young's modulus is E, and again the temperature is increased by T degree Celsius, and it is restricted by these two supports. It is restricted by the supports like this. Okay. So due to this delta T, again the thermal stress sigma dash will be produced here. I am taking this as sigma dash. The thermal stresses produced here will be sigma dash. So again for this scenario, I can write down delta net along x is equal to 0. So delta net along x is equal to 0. So delta net is free expansion minus effect of sigma dash, and sigma dash is the thermal stress that is produced for this length. Okay, free expansion will be 2L into alpha into delta T minus sigma dash upon E into 2L, that is equal to 0. So from here, what is the value of sigma dash? Sigma dash is again coming out as E alpha T, and E alpha T is nothing but your sigma. So even with the change in length, what will be the change in thermal stress? There will be no change. Even after increase in length, the thermal stress produced will be same as the initial thermal stress. So sigma dash will be equal to sigma here. So for this question, your option A is the correct answer here. So option A is the correct answer here. Let me see, is there any other question from chapter 1? Okay, so this ends our first chapter of simple stresses and strain. Okay, sir. Now after this, we have one fantastic chapter. Very good. We have one fantastic chapter. Yes, Manav, you want to ask something? Do you have any question you can ask? So you have this fantastic chapter of shear force and the bending moment diagram. Just let me quickly revise this: shear force and bending moment diagram, SFD and BMD. If you see the gate score booster sessions, I have dealt this chapter in detail. We have seen so many questions from shear force and bending moment diagram. But in this revision cycle, what I want to tell you is, first of all, if you want to find out the support reaction, what is the tool that we will going to use for calculating the support reactions? For calculation of support reactions, what is the tool we will going to use? For calculating support reactions, we will going to use the equations of static equilibrium. The equations of static equilibrium. The equations of static equilibrium. Static equilibrium. The equations of static equilibrium means summation of horizontal forces equal to 0, summation of vertical forces equal to 0, summation of moment about any point, equal to 0. So these are the three basic equations of static equilibrium. Related to this, if any internal hinge is present, special case here, if internal hinge is present, special case is of internal hinge. Special case is of internal hinge. Internal hinge. If internal hinge is present, so what advantage we get? A special case is of internal hinge. So if internal hinge is present, what is one advantage? For example, if this is your beam, let me take any beam like this. This is one beam here. Say this is a beam, and for this beam, internal hinge is present at this point. Say this point is A, B, C and D. So when internal hinge is present, what is that one advantage we get? One advantage is, if I have to apply the equation of static equilibrium, that will be summation of moment about C equal to 0. Means in this case, I have to stand at C and I have to write down summation of moment due to all the loads throughout the entire length of the beam, right? So when you write this summation of moment about C equal to 0, you have to consider the entire length. You have to consider entire length of the beam. But when internal hinge is present, one advantage that we have is summation of moment about C on portion CA. So when you write this equation, it means you have to stand at C and you have to only observe the left side of C. From C to A you have to observe. From C to A. From C to A you have to see. From C to A you have to see. Similarly, when you write down summation of moment about C on portion CD equal to 0, means you have to stand at C and observe the right side, only right side. So from C to D you need to move. From C to D you need to move. From C to D you need to move, right? Last year in mechanical engineering we had one question where they asked which of the following structure is the determinate or indeterminate structure. Now sir, how to decide that? If the structure is statically determinate, if the structure is determinate, it means that the number of support reactions are less than or equal to the number of equilibrium equations. Number of support reactions are less than or equal to number of equilibrium equations. Okay sir. If the structure is indeterminate structure, if the structure is a determinate structure, then the number of support reactions are less than or equal to the number of equilibrium equations. If the structure is indeterminate structure, for indeterminate structure, the number of support reactions are more than or equal to the number of equilibrium equations. Sorry, more than number of equilibrium equations, not equal to number of equilibrium equations, right? So if number of equilibrium equations are less, structure is indeterminate. If number of equilibrium equations are more, structure is determinate. I will draw one beam. Can you tell me whether it is determinate or indeterminate quickly? I am drawing one beam like this, whether it is determinate or indeterminate. Quickly tell me. It's a propped cantilever beam. Determinate or indeterminate? You have to comment. Then this one. You have two beams in front of you. Quickly tell me which one is determinate, indeterminate, like you can say. First beam is determinate or indeterminate? Tell me that. First one is determinate or indeterminate? Quickly. First one is indeterminate. Very good. The number of support reactions here are how many? 1, 2, 3 support reaction, then here 1. So in total you have 4 support reactions. How many equilibrium equations? You have 3 conventional equilibrium equations. R is more than E. Therefore it is an indeterminate structure. Second one. Tell me about the second one. Determinate or indeterminate? Tell me about the second one. Determinate or indeterminate? You have 2 internal hinges in the second structure. Please tell me determinate or indeterminate? Second one. How many support reactions here? How many support reaction for this beam? First tell me the support reaction, then I'll tell you about. Manav is saying determinate. Okay. How many support reactions, Manav sir? Can all of you tell me how many support reactions you are observing for this particular beam? How many support reactions? Quickly give your answers. I'm waiting for your answers. Quickly give it. How many support reaction for this particular beam? 5 support reactions you have. So 1, 2, then 3, then you have 3 more support reactions here. So in total you have 6 support reactions here. R is equals to 6. Okay. Now talking about the number of equilibrium equations, for that you need to see in this beam you have 3 conventional equilibrium equation, but 1 additional equilibrium equation due to this internal hinge and 1 more additional equilibrium equation due to this internal hinge. So you have 2 additional equilibrium equations, therefore this is 5. So number of equilibrium equations are 5 and the number of support reactions are 6. Again, support reaction is more than equilibrium equation. So this is also your indeterminate structure. This is also your indeterminate structure. Civil students, they calculate degree of static indeterminacy. Mechanical student, this much is sufficient for you. Okay. So let's see this question. Please try this. You have 2 minutes of time. Go for it and get me the answer. It's an easy question. Don't commit a mistake. Go for it. Means from this only you can understand the first important areas from where the questions are asked is the simple stress and strain, and the second important area is the shear force and the bending moment diagram. Okay. Go for it, go for it. Go for it. Kindly keep commenting your answers. Keep commenting your answers. Keep commenting your answers, whatever answers you are getting. Yeah, Parthiv is saying option C. Okay, sir, let's see. Parthiv sir is saying option C. Okay. All of you keep commenting your answers. Keep commenting your answers. I hope whatever we are discussing, you are able to recall properly whatever you have read previously, I think. Do it, all of you just keep commenting your answers. So the question says that for a simply supported beam of length L, subjected to a uniformly distributed moment. Uniformly distributed moment means moment intensity is given to you. Kilonewton meter per meter is given to you, right? Uniformly distributed moment as shown in the figure, the bending moment at the mid span of the beam is. You need to find out bending moment at L by 2. It's very simple. First thing is find out the support reaction at both the ends. So let me have this beam here. So this is your simply supported beam which is subjected to the moment intensity, concentrated moment intensity of M. So concentrated moment intensity of M, this beam is subjected to like this. This is M kilonewton meter per meter, right? The length of the beam is given to you as L. Let me take few points. This is point A, this is point B, and the midpoint here is point C. And the distance between A and C is L by 2 and C and B is also L by 2. So first thing, for finding out bending moment at this point C, you need to calculate the support reaction at A and B. So support reaction at A and B, right? So first of all, decide the direction of support reaction. So all these moments are trying to rotate the beam in the clockwise direction. So the support reaction should form anti-clockwise couple. So for forming the anti-clockwise couple, VB should act upwards and VA should act downwards like this. Okay, sir. So this is how, first of all, I have figured out the direction of this support reaction, and this is your HA, which is of no use. So you can first write down, for calculating support reaction, summation of horizontal forces equal to 0. So therefore HA is equals to 0. Now second is, you can write down summation of moment about B equal to 0. So when you write down summation of moment about B, observe the left side, right, this entire beam. What is the total moment? This total moment is M into L, and this total moment is acting in the clockwise direction about point B. So total moment is M into L acting in the clockwise direction, so M into L, and this VA will going to give you the anti-clockwise moment about B. Value will be minus VA into L, and this should be equal to 0. So from here the value of VA came out as M. VA is equal to M. So support reaction at A came out equal to M, right? Now only VA is required. What you will need to do is stand at this section C and write down the bending moment over this section C. So bending moment at C is equal to, bending moment at C is equal to, bending moment at C is equal to, first of all, this VA will going to give you the hogging moment at C, and the value of that hogging moment will be equal to VA into L by 2. So VA into L by 2 is the hogging moment at C. Then this moment intensity will going to sag the beam, and what is the total moment that is acting over this section XX at C? That is equals to M into L by 2, and it's a sagging moment. So plus M into L by 2. So just now you calculated VA is equals to M. So this is minus ML by 2 plus ML by 2, and minus ML by 2 plus ML by 2 is equal to 0. So bending moment at C is equal to 0, right? So a simple question, but a 2-mark question. Complicated for those students who have directly approached this question without giving a much thought, right? So sometimes the question will require a sense of understanding here. Let's move ahead with this. This is another question. Please try it. The question says that you need to find out the vertical support reaction at X. You need to find out the vertical support reaction here at X. Internal hinge is present here. Loading, everything is given to you. Go for it. Have 2 minutes of time. Try this and calculate the support reaction. Because this type of propped cantilever beam with internal hinge is asked for many times in mechanical and civil. All of you just quickly give me an answer. Go for it, go for it. Any answers? Any answers, anyone? A propped cantilever beam with internal hinge is given to you. Intensity here is 10 kilonewton per meter. Any answers, anyone? Okay. So this is the beam. Let me draw the beam. This is 2 meter everywhere, and 10. This is your internal hinge, and the intensity is acting like this. Now it's a very easy question, right? Now understand this, how we need to approach this. 10 kilonewton per meter. This is 2 meter, and this is also 2 meter. This is your x, this point is y. Let me take this point as z. Okay, sir. Now what is the problem here? Problem here is, if you write down summation of vertical forces equal to 0, then both these support reactions will come. So vertical reaction here is Vx, and vertical reaction here is Vy. Both these vertical reactions will come, right? If you take summation of moment about x equal to 0, then this moment reaction mx will come into play, right? And then you have this horizontal reaction hx. So I have to find out the value of Vx, but here I will going to calculate all the support reaction, because in many questions we have seen that they are asking moment reaction, they are asking support reaction here, they are asking support reaction here. So I will going to calculate all the support reaction in this case, right? First of all, for calculating this hx, I will write down summation of horizontal forces equal to 0. So that eliminates hx. So hx comes out as 0. Right, now directly don't use summation of vertical forces, because this Vx and Vy will both come into moment about z. Very good. So we will take summation of moment about z on portion zy equal to 0. Summation of moment about z on zy equal to 0. So when we do this, you will have to have the first clockwise moment due to this UDL. Value will be 10 into 2 is the total load into 1. So 1 is the distance between CG of this UDL and point Z. The second moment will be due to this Vy, and it is an anti-clockwise moment. So Vy into 2, that is equal to 0, right? So from here the value of Vy came out as 10 kilonewton. This is the value of Vy. But they want the value of Vx. So now take the summation of vertical forces equal to 0. When you take summation of vertical forces equal to 0, you have Vx acting upwards, Vy acting upwards, and this UDL acting downwards. So minus 10 into 4, and that is equal to 0. So the value of Vy you have already calculated as 10. So Vx is equal to 40 minus 10. So 40 minus 10 is coming out as 30 kilonewton. Okay, so don't commit the silly mistakes here. This is 20. Why it will be 20? 10 into 2 into 1 minus Vy into 2. Why this will be 20? This is 10. Bhaiya ji, this is 10. Just check once again. This is 2, this is 2, this is 10, yeah. So this will be 10 here. Why 20? Yeah, calculation mistake, Manav sir. Okay, this is correct. Vy is 10 and Vx is 30. Everyone. This is fine. Vx is 30 and Vy is 10. Just confirm me once. Yeah, I think it is correct. Absolutely. Now the next thing is, you want this mx. Now for calculating this mx, there are two things. Either you can write down summation of moment about x equal to 0, or you can write down summation of moment about z on portion zx equal to 0. Whichever is easy, you can have. Okay. So I will apply both of them. This is more difficult for most of you, so I will use this. So summation of moment about z on portion zx is equal to 0, right? So first you will going to have a clockwise moment due to this Vx. Value will be Vx into 2. Then second will be this anti-clockwise moment mx, so minus mx. Don't start multiplying mx into 2. I have seen many students doing this kind of mistake. This is a concentrated moment reaction, so don't multiply it with the distance, right? Distance will be always coming with the load. So first one is Vx into 2, second one is mx minus, and then this UDL will going to give the anti-clockwise moment. My value will be minus 10 into 2 into 1. and this is equal to 0. So from here you can find out the value of mx. So mx is equal to Vx is 30. So 30 into 2 minus 20. So 30, 60, 60 minus 20, 40. Mx is 40 kilonewton meter. Mx is coming out as 40 kilonewton meter. This is the value of mx here. Okay. So like this you can find out any of the support reactions, any. Only Vx was asked, but we have calculated all the support reactions so that if any question comes from this area, you can solve it properly. Let's move ahead with this. Please try this fantastic question. It's a 2-mark question for 22. Go for it. Two minutes of time for you. Go for it, go for it. Reason why I am taking all these previous year questions, because already you people have done it for 2-3 times. So just check whether you are recalling the questions or not. Recalling the approach or not, I should be correct on this. Go for it. Go for it, go for it. Please go for it. Go for it, everyone. So a semicircular bar of radius r meter in a vertical plane is fixed at end G as shown in the figure. A horizontal load of magnitude P kilonewton is applied at the end H here. The magnitude of the axial force, shear force and bending moment at a point Q, theta is equals to 45 degree respectively R. So at this point Q, you need to find out the value of axial force, shear force and the bending moment. Okay, sir. So what we will going to do is, we will going to consider this portion, HQ, this portion HQ. So this is the portion HQ like this. This is the portion HQ and it is subjected to a load of P here. Okay, this angle here is 45 degrees. This angle here, theta is equals to 45 degrees here. This is H, this is point Q. Now check this out. Over this Q, the shear force will be acting in this way. This is the shear force at Q. Okay. And this is your axial force at Q. So this is 45 degrees and this is also 45 degrees. This is your axial force at Q and this is your shear force at Q. So I have drawn the free body diagram for this H to Q, right? This radius is R here and this radius is also R. Now the next thing that I have to do is, I have to simply write down summation of horizontal and vertical forces equal to 0, and that will going to give me the value of axial force and shear force at Q. So first I'll start with the summation of vertical forces equal to 0. So summation of vertical forces equal to 0. So that will going to give me axial force at Q into sine 45 degrees. Axial force at Q into sine 45 degrees is equal to, minus shear force at Q into sine 45 degree, but with a minus sign because it is acting downward. Minus shear force at Q sine 45 degrees. So from here, axial force at Q is equal to shear force at Q. So from the first equation, we got this relation that axial force and shear force both are same. Second is, you can write down summation of horizontal forces equal to 0. So you have P acting this side, and then you have axial force at Q cos 45 plus shear force at Q cos 45, and that will going to give you the value. Okay, let's see this. So summation of horizontal forces equal to 0. So you have minus P plus axial force at Q into cos 45 degrees plus shear force at Q into cos 45 degrees is equal to 0. Now this axial force at Q and shear force at Q are same, so I can write down axial force at Q into cos 45 degrees into 2 is equal to P. So cos 45 is 1 by root 2, substitute and get the answer. Axial force at Q is equals to shear force at Q is equal to, this will be P by root 2 in kilonewton. So this is your axial force and shear force at Q, P by root 2 in kilonewton. After this, you can calculate the bending moment at Q. Check this out. So for calculating the bending moment at Q, stand at Q. So bending moment at Q, I am writing here, bending moment at Q is equal to P into this distance, this. From here to here, this distance. What is this distance? What is this distance? This is the lever arm for this load P, and this distance is R sine 45. So bending moment at Q is equal to bending moment at Q is equals to P into R sine 45, this distance. So bending moment at Q is equal to P into R sine 45, and sine 45 is 1 by root 2. So bending moment at Q is equal to P into R by root 2. This will be in kilonewton meter. So like this, you need to deal with these type of questions, especially from the arches. So you have to consider the part and draw the free body diagram, and then apply the equations of static equilibrium over that portion. Okay, let's move ahead with this. Try this question. Now before trying this question, I would just like to give you one table. Please understand this. If you apply the load over any beam, for example, if this is my beam and under the action of load, under the action of some load, this beam is deflecting like this, right? So this is termed as the deflection of the beam, and you can see this deflection of the beam is the function of x. So first of all, deflection y is the function of x. So deflection of the beam under the action of load will be the function of x. The slope at any point theta is equal to dy by dx. The slope at any point theta is equals to dy by dx. Then bending moment or the curvature, is equals to d theta by dx, is equal to d theta by dx, which is also equal to d2y by dx square, which is also equal to d2y by dx square. Now comes the very important part. The slope of bending moment diagram, dBm by dx, the slope of bending moment diagram is equal to the shear force. The slope of bending moment diagram is equal to the shear force, and last is the slope of shear force diagram is minus times of intensity of loading. The slope of shear force diagram, dsf by dx, the slope of shear force diagram is minus times of intensity of loading. This chart you should remember, because from this chart a good quality question can be asked, right? From this chart a good quality question can be asked. Always remember this chart. Always remember this chart. So 2 points here. I will write these 2 points in block. First one is slope of bending moment diagram is shear force, Second, add the section of at the section of maximum bending moment, maximum or minimum I should write, at the section of maximum or minimum bending moment, shear force will be 0. Okay. At the section of maximum or minimum bending moment, shear force will be 0. Very good evening, Richa. Very good evening. Then after this, one more thing, point of contraflexure. What is point of contraflexure? Point of contraflexure means that point. Point of contraflexure means that point where bending moment diagram changes its sign. So point of contraflexure is that point where bending moment diagram changes its sign. Bending moment diagram changes its sign. Bending moment diagram changes its sign. That is termed as the point of contraflexure. Okay. Now let's see this question. The question says that the bending moment diagram for the beam is given below. This is the bending moment diagram for the beam. They are asking to calculate the shear force at section AA dash and section BB dash. So if bending moment diagram is given to you, from this bending moment diagram, how can you calculate shear force at a particular section? So always remember that the shear force at a particular section is equal to the slope of bending moment diagram. Slope of bending moment diagram. Shear force at a particular section is equal to the slope of bending moment diagram. If this is your bending moment diagram, what is the slope at section AA? Anyone? What is the slope of this bending moment diagram at section AA dash? Quickly. What is the value of slope at section AA dash for this bending moment diagram? Chalo, quickly everyone please tell me. What is the slope at AA dash? The slope here is equal to 0. So simply in one line I will write down, since the slope of bending moment diagram here is 0, therefore shear force at this section AA dash is equal to 0. So shear force at AA dash is equal to 0. We got the first answer. Now tell me what will be the slope at this section BB dash. What is the slope at this section BB dash? What is the slope at section BB dash? Quickly. What is the slope at section BB dash? Please tell me the answer here. What is the slope of this bending moment diagram at BB dash? It is 50. Okay, let's check. So you can see here, for calculating the slope, let me draw one line like this. So this value will be how much? From here to here, this value will be 200 minus 100. So 200 minus 100 will be 100. And this here is 2 meter. So the slope at BB dash, that is equal to the shear force at BB dash. Shear force at BB dash is equal to the slope of this bending moment diagram, which is equals to 100 by 2, and the answer is 50. Just see in one line, those students who have read the same concept from the conventional point of view, how difficult it could be, right? But you have just solved in one line. So whenever bending moment diagram is given to you and you are asked to find out the shear force, calculate slope of that bending moment diagram at that particular section. Let's move ahead with this. Try this question. Okay, before moving into this question, I think I have one more here. Just wait. Okay, we are going to see this. Okay, meanwhile, can you just try this question? You can try this question. So we finished the two very important topics of shear force and bending moment diagram, but now it's time for this. If time will permit, I will also give you the shear force and bending moment diagram for the standard cases, right? But first we need to deal with all this. Solve this question. Do it, everyone. Chalo, you might be feeling कि this question is such a complicated question, sir. It is asked in GATE 23 last year. How to solve such questions? So this question is first of all from the chapter of principal stresses and strain. Let's see this. So you can make a formula sheet like this. You can give the heading principal stresses and strain. Principal stress and strain. This is the name of the chapter. And then you have first stresses on the oblique plane. First one is the stresses on the oblique plane. So you have a complex state of stress, and for the complex state of stress, it is subjected to normal and shear stresses like this. So for this complex state of stress, it is subjected to normal stress in x direction sigma x, normal stress along y direction is sigma y. Then you have shear stress tau xy acting like this, tau yx acting like this, tau yx, and then you have tau xy acting like this. So this is sigma x, this is tau xy, this is tau yx, this is sigma y, this is also sigma y, this is sigma x, this is tau xy, this is tau yx, right? So for this complex state of stress, you need to find out the value of normal and shear stress on this oblique plane. And this oblique plane is inclined at an angle of theta from this reference plane. So AB will be my reference plane first of all, and this AC is the oblique plane over which normal stress sigma n and shear stress tau will be acting. Normal stress sigma n and shear stress tau will be acting here. For this state of stress, we have a set of sign convention, and based on that sign convention only, we will going to write down all the formulae. Now, sir, what is the sign convention that we use? So for normal stresses, tensile is positive, and compressive is negative. For normal stress, tensile is positive and compressive is negative. Now talking about the shear stress. So for deciding the direction of shear stress, you have to observe this reference plane, right? For deciding the direction of the shear stress, you need to observe this reference plane. Over the reference plane, if the shear stress gives the clockwise sense of rotation like this, then this shear stress will be taken as positive. You have to observe this reference plane AB, right? So over this reference plane, if the shear stress gives the clockwise sense of rotation, it is positive. But if the shear stress gives the anti-clockwise sense of rotation on the reference plane AB, then it is taken as negative. So if the shear stress is acting like this, which is giving the anti-clockwise sense of rotation, then it is taken as negative. Similarly, on this oblique plane, if the shear stress gives the clockwise sense of rotation over this oblique plane AC, if the shear stress gives the clockwise sense of rotation, then it is taken as positive. But over this oblique plane, if the shear stress gives the anti-clockwise sense of rotation, then it is taken as negative. So these are the sign conventions that we use for normal stress and shear stress. One more sign convention we use for this theta. From this reference plane, if theta is measured in the clockwise direction, then it is positive. Or from the vertical, if the angle of the oblique plane is measured in the clockwise direction, then it is positive. But if it is measured in the anti-clockwise direction, then it will be negative. So for angle of the oblique plane, For angle of oblique plane, this is the sign convention we use. So for example, if this is the vertical, and from the vertical, if the angle of the oblique plane is in the clockwise direction, then it is positive. If this angle of the oblique plane from this vertical, if the angle is measured in the clockwise direction, then it is positive. From the vertical, if it is measured in the anti-clockwise direction, then it is negative. So based on these sign conventions, we will going to write down all the formulas for the stresses in the oblique plane: normal stress, shear stress, principal stress, maximum shear stress, position of principal planes, position of plane of maximum shear stress, all those things. These sign conventions should be used, right? Apart from this, no other sign convention we will be using. So first of all, normal stress on the oblique plane, sigma n, is equal to sigma x plus sigma y by 2, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. This is your normal stress on the oblique plane. So what is normal stress on the oblique plane? Sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. Similarly, shear stress on the oblique plane is equal to minus of sigma x minus sigma y by 2 minus of sigma x minus sigma y by 2 into sin 2 theta plus tau xy cos 2 theta. So these are your normal stress and shear stress on the oblique plane. Now you can see this shear stress and normal stress on the oblique plane. Shear stress and normal stress on the oblique plane varies with the value of theta. Okay. For different values of theta, you will get different values of normal stress and shear stress, right? How many planes are there? Infinite oblique planes are there for different values of theta. Now out of these all the oblique planes, there will be two planes which are mutually perpendicular to each other, over which the value of shear stress will be equal to 0. Again, let me confirm, we are talking about 2D loading, right? You can see this, all this loading is taking place in 2D. So for this 2D loading, there will be two planes over which shear stress will be equal to 0. Such planes are termed as principal planes. So for 2D, for 2D loading, there will be two principal planes. There will be two principal planes. There will be two principal planes. And what are principal planes? Principal planes are those planes over which shear stress is equals to 0. Similarly, for 3D loading, we have three principal planes. And all these principal planes are mutually perpendicular to each other. They are mutually perpendicular to each other. They are mutually perpendicular to each other. Mutually perpendicular to each other. They are mutually perpendicular to each other. Now the normal stress acting on the principal plane is termed as principal stresses. So the highest value of normal stress is termed as major principal stress, and the least value of normal stress is termed as minor principal stress. So sigma 1 is termed as major principal stress, and sigma 2 is termed as your minor principal stress. This is your minor principal stress. The value of sigma 1, 2 can be calculated as sigma x plus sigma y by 2 plus minus under root of sigma x minus sigma y by 2 the whole square plus tau xy square. This is the value of major and minor principal stress. Plus can be used for major and minus can be used for minor principal stress, right? Now after this, the location of these principal planes can be found using this expression. The location of principal plane can be found using this expression. Location of principal plane is location of principal planes can be found using this expression. So theta 1 is equal to 1 upon 2 into tan inverse of 2 tau xy upon sigma x minus sigma y upon sigma x minus sigma y. This is the location of first principal plane. Similarly, the location of another principal plane theta 2 will be equal to theta 1 plus 90 degrees. Okay. So if you have calculated theta in radians, then this will become pi by 2, right? So these are the location of two principal planes. This entire story is for 2D. If you have 3D state of stress, for 3D state of stress, there will be three principal planes and there will be three value of principal stresses. So you can write a note here for 3D loading. For 3D loading, there will be three principal planes, three mutually perpendicular principal planes. Three mutually perpendicular principal planes, and there will be three principal stresses. Sigma 1 will be the major principal stress, then sigma 2 here is intermediate principal stress, and sigma 3 will be minor principal stress. This will be minor principal stress, right? Calculation of sigma 1, sigma 2 and sigma 3 is not the part of your syllabus, but this much of information is sufficient, right? So if any such question comes that for 3D loading, how many principal planes will be there? So there will be three mutually perpendicular principal planes, right? Now after this, you have in 2D loading, you have two principal planes. There will be two more planes over which shear stress is maximum, and those are termed as planes of maximum shear stress. So there will be two mutually perpendicular planes of maximum shear stress. So for 2D loading, there will be two mutually perpendicular planes of maximum shear stress. Right? Now sir, how to find out the location of planes of maximum shear stress? Location of planes of maximum shear stress. Location of planes of tau max. Location of planes of tau max. So location of planes of tau max can be found out using this. Phi 1 is equals to 1 upon 2 tan inverse of minus of sigma x minus sigma y upon 2 tau xy. So this is the location of plane of maximum shear stress, first location. Second location, phi 2 is equal to phi 1 plus 90 degrees. Both of them are mutually perpendicular, therefore phi 1 plus 90 degree will be the value of phi 2. Okay sir, once you have got this value of tau max, so the maximum shear stress tau max is equal to sigma 1 minus sigma 2 divided by 2. Sigma 1 minus sigma 2 divided by 2. The same tau max can be also calculated as under root of sigma x minus sigma y by 2 the whole square plus tau xy square. Sigma x minus sigma y by 2 the whole square plus tau xy square, that is also equal to tau max, right? If you remember, this is nothing but the radius of the Mohr circle, okay? This is also the radius of the Mohr circle. Last one is normal stress on the plane of maximum shear stress. Normal stress on the plane of maximum shear stress is equals to sigma 1 plus sigma 2 divided by 2. Normal stress on the plane of maximum shear stress is equal to sigma 1 plus sigma 2 divided by 2. So these are very important formulas. Along with this, there is one note point here, and the note point says that sum of the normal stresses acting on two mutually perpendicular planes is a constant. Means sigma x plus sigma y is equal to sigma 1 plus sigma 2 is equal to sigma theta, normal stress acting on the oblique plane, theta plus sigma theta plus 90 degree will be same. Always remember this, sigma x plus sigma y is equals to sigma 1 plus sigma 2 is equals to sigma theta plus 90 degree, right? So this sum is a constant. Now these are all the expressions for stresses. Using the expressions for stresses, we can write down the expressions for strain, right? What you need to do is, wherever normal stress is acting, wherever normal stress expression is there, substitute it with the normal strain. Wherever shear stress is there, substitute it with the shear strain by 2. Substitute it with shear strain by 2. So you can write down all the expressions for strains. So on the oblique plane, you can write down the normal strain. On the oblique plane, you can write down the shear strain, right? So you can write down this strain expressions. So strains can be written like this. Normal strain on the oblique plane is equal to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 into cos 2 theta plus phi xy by 2 into sin 2 theta. Similarly, shear strain on the oblique plane phi by 2 is equal to epsilon minus of epsilon x minus epsilon y by 2 into cos 2 theta into sin 2 theta plus phi xy by 2 into cos 2 theta. Okay. Similarly, you can find out major principal strain epsilon 1 is equals to epsilon x plus epsilon y by 2 plus under root of epsilon x minus epsilon y by 2 the whole square plus phi xy by 2 the whole square. Similarly, you can write down epsilon 2 is equal to epsilon x plus epsilon y by 2 minus under root of epsilon x minus epsilon y by 2 the whole square plus phi xy by 2 the whole square, right? So this is the value of major and minor normal strains, right? Then you have maximum shear strain phi max is equal to epsilon 1. So phi max by 2 I am writing. Phi max by 2 is equals to epsilon 1 minus epsilon 2 by 2. So from here the value of phi max will come out as phi max will be epsilon 1 minus epsilon 2. And the last here is normal strain on the plane of phi max is equal to epsilon 1 plus epsilon 2 by 2. This is the normal strain on the plane of phi max. You can write this normal strain on the plane of phi max. So these are all the values of strain that can be asked in your examination. Let's move ahead with this. So this is the first question coming up here. I think we have missed the first question. This was the first question here. This is the first question. The first question says that the infinitely small element shown in the figure not to the scale represents the state of stress in a point in a body. What is the magnitude of maximum principal stress? They are asking you to calculate the value of maximum principal stress. How we can calculate this? So first of all, identify this. In this diagram, what is given to you? You are given with the value of sigma y, which is 6 kilonewton per mm square. So the value of sigma y is given to you as 6 Newton per mm square. Okay, sir. Then this is your oblique plane, right? Over this oblique plane, normal stress is 5 Newton per mm square and the shear stress is 4 Newton per mm square, and this shear stress on the oblique plane is giving the anti-clockwise sense of rotation. So I will write down normal stress on the oblique plane is equal to 5 Newton per mm square and shear stress on the oblique plane is minus 4 Newton per mm square. Okay. Now check one very important thing here. This is tau yx. So tau xy will be acting like this, right? So this is my reference plane. Over this reference plane, this tau xy is giving the anti-clockwise sense of rotation. So this will be minus 3 Newton per mm square. So the value of tau xy is minus 3 Newton per mm square. Okay. Now this oblique plane measures its angle from the vertical in the anti-clockwise direction. So this angle here is minus 45 degree or minus theta. So theta here is minus 45 degrees. Theta here is minus 45 degrees. So you have all the sufficient information to find out the value of major principal stress. But for calculating major principal stress, you should know the value of sigma x. So first, for calculating the value of sigma x, you can use any of the expression for normal or shear stress on the oblique plane. So I'll use this shear stress on the oblique plane is equal to minus of sigma x minus sigma y by 2 into sine 2 theta plus tau xy cos 2 theta plus tau xy cos 2 theta, right? Tau is equals to minus 4. This is equals to minus of sigma x, sigma y is 6 by 2 into sine of minus 45, twice of minus 45 degrees. So this will be sine of minus 90 degree. Sine of minus 90 degree will be minus sine 90. So this will be sine of minus 90 degrees plus tau xy. Tau xy is minus 3 into cos of minus 90 degrees, right? So this minus sign will come out. So this will become plus here. So you have minus 4 into 2 minus 4 into 2 plus 6 is equal to sigma x, because sine 2 theta, sorry, sine 90 will be 1, sine 90 is 1, and this cos 90 will be 0. So what will be the value of sigma x here? Sigma x is coming out as how much? Sigma x is minus 2. Just confirm this, sigma x is minus 2. Kindly confirm this. What is the value of sigma x here? Is it minus 2 or what? Kindly confirm this. What is the value of sigma x? Is it minus 2 or something else? So 4 to the 8, 8 plus 6, minus 8 plus 6 will be minus 2. Yeah, sigma x is, I think, coming out as minus 2. Now, since you know the value of sigma x, now you can calculate the value of sigma 1. So sigma 1 is equals to sigma x plus sigma y by 2 plus under root of sigma x minus sigma y by 2 the whole square plus tau xy square. So you have sigma 1 is equal to sigma x is minus 2, sorry, sigma x is minus 2, sigma y is 6. So minus 2 plus 6 plus under root of minus 2 minus 6 by 2 plus tau xy is how much? Tau xy is minus 3. This will be minus 3 square. Please calculate this value of sigma 1. So this is equals to sigma 1. This is 4. 4 by 2 will be 2. 2 plus under root of this will be 8. 8 by 2 will be 4. So 4 square plus 3 square will be 5. Under root of 4 square plus 3 square will be 5. So the value of sigma 1 is coming out as 7 megapascal. This is the value of sigma 1, and sigma 1 is coming out as 7 megapascal. All of you just confirm this. Is it the same answer you are getting or something else? Same answer or something else? Just kindly confirm this. Sigma 1 is 7 megapascal. Okay. Let's move ahead with this. Next question will be here. Okay. So the question says that the state of two-dimensional stresses acting on a concrete lamina consists of a direct tensile stress sigma x of 1.5 Newton per mm square and the shear stress tau of 1.2 Newton per mm square, right? Which cause cracking in concrete, then the tensile strength of the concrete in Newton per mm square is. So first of all, understand what is the state of stress given to you. You are given with sigma x of 1.5 Newton per mm square and the shear stress tau is 1.2 Newton per mm square, which cause the cracking of the concrete. Okay, sir. So this is the state of stress that is given to you. This is a concrete block over which the normal stress sigma x and tau xy is acting. So this is sigma x here, and this is tau xy, this is tau yx, this is again tau xy, this is tau sigma x, this is tau yx, right? Now, sir, where the crack will develop? First of all, the crack will develop over that plane on which the normal stress acting is maximum, right? So means we are talking about that oblique plane over which normal stress acting is maximum. And we know that the plane over which normal stress acting is maximum is termed as major principal plane, right? So that oblique plane over which normal stress acting will be maximum will be the major principal plane, and they are asking you to find out the value of this major principal stress of sigma 1. They are asking you to calculate the value of major principal stress sigma 1 because that will corresponds to the strength of concrete, right? So when the normal stress reaches sigma 1, then only the crack will develop over this plane. So you can calculate that sigma 1 is equals to sigma x plus sigma y by 2 plus under root of sigma x minus sigma y by 2 the whole square plus tau xy square. So here the value of sigma x is given to you as how much? Sigma x is 1.5 and this is 1.2. So sigma x is 1.5, sigma y is 0. So 1.5 plus 0 by 2 plus under root of 1.5 minus 0 by 2 the whole square plus 1.2 square. You can calculate this and that will going to give you the strength of concrete. Please calculate this value and tell me the answer. So 1.5 divided by 2 whole square plus so this is coming as 2.165. So this sigma 1 is coming as 2.165 Newton per mm square. So this will be the strength of concrete that they are asking, right? This is the strength of concrete that they are asking. Let's move ahead to the next question. This is the next question which says that the state of stress represented by the Mohr circle shown in the figure is. So first of all, which state of stress will represent this Mohr circle? So you have four options. First one is biaxial tension of equal magnitude. So for example, if you have the state of stress like this, biaxial tension means this. The normal stress acting in x and y direction are same, and even the magnitude wise and the direction wise they are same. So this is the biaxial tension. For this biaxial tension, if you remember how to draw the Mohr circle, first of all consider two planes which are mutually perpendicular to each other in the clockwise direction. Consider two planes which are mutually perpendicular to each other in the clockwise direction, means this angle should be 90 degree, right? So what are the coordinates for plane AB? You can observe this for plane AB. Only normal stress is acting, there is no shear stress acting. So for plane AB, the coordinates will be sigma comma 0. Now come to this plane AD. For plane AD, again there is no shear stress, only normal stress is acting. So this will be the coordinate for plane AD. You have to plot, when you plot these 2 points, you will find out that for biaxial state of stress, the Mohr circle is a point circle whose center is at sigma comma 0 and radius is equals to 0. This is the Mohr circle for this state of stress whose center will be at sigma comma 0. This will be the center of the Mohr circle, and the radius for this Mohr circle will be equal to 0. Radius here is 0. What is the important thing about this type of Mohr circle? This type of Mohr circle indicates that all the planes that are present in this state of stress are termed as principal planes. So for this state of stress, you have infinite principal planes, okay? Because all the planes will have only normal stress, there will be no shear stress. So for this type of loading, you have infinite principal planes and the radius of the Mohr circle will be 0 and it's a point circle. This is your shear stress axis and this is your normal stress axis. Then next one is your uniaxial tension. So for example, if you have the state of stress like this, for this state of stress, it is subjected to uniaxial tension sigma. Okay, so this is your plane AB and plane AD. So what is the coordinate for plane AB? Can you tell me what are the coordinates for plane AB? So for plane AB, the coordinates will be sigma comma 0. And for plane AD, you can see no stress, so coordinates will be 0 comma 0. So for this state of stress, the Mohr circle will be like this. This will be the Mohr circle here. So this is your major principal stress sigma comma 0 and your minor principal stress will be 0 comma 0. So where will be the center of this Mohr circle? The center of this Mohr circle will be at a distance of sigma by 2 comma 0, right? And the radius of this Mohr circle will be equal to sigma by 2. Radius of this Mohr circle is equal to sigma by 2. These are the points which represents the plane of maximum shear stress. So for this loading, the maximum shear stress here will be equal to, the coordinates of this point will be sigma by 2 comma sigma by 2, and this will be sigma by 2 comma minus sigma by 2. One more thing I just like to remind you, that the radius of the Mohr circle will be always equal to the maximum shear stress, okay? So for two loadings, we have seen the Mohr circle and none of them matches with this. Now comes the state of pure shear. For the state of pure shear like this, a state of pure shear like this is the state of pure shear. For this state of pure shear where only shear stresses is acting and no normal stress are acting, for this state of pure shear, the Mohr circle that you will get, let's see, this is the state of pure shear. This is the state of pure shear. This is A, B, and this plane is D, and this angle is 90 degree. So this is tau here, this is also tau here, and tau here. This is the state of pure shear. For plane AB, what will be the coordinates? The shear stress is giving the clockwise sense of rotation, so this will be 0 comma tau. And for plane AD, the coordinates will be how much? This tau is giving the anti-clockwise sense of rotation, so this will be 0 comma minus tau. So when you plot these 2 points, you will get a Mohr circle like this. This will be the Mohr circle for this state of stress. So the center of this Mohr circle will be at 0 comma 0. The radius of this Mohr circle will be tau, and all these point coordinates, this will be tau comma 0, means your major principal stress is tau. This will be 0 comma minus tau, this will be 0 comma plus tau, and this will be minus tau comma 0. And this is the state of, this is the Mohr circle for this state of stress. This is shear stress sigma, and this is your normal stress sigma n, right? So you can see for this Mohr circle, the state of pure shear is the correct answer. So for this Mohr circle, the state of pure shear is the absolutely correct answer. The fourth option says that hydrostatic stress. Hydrostatic stress means the compressive stresses of equal magnitude are acting over the material, right? So again, for this hydrostatic stress, it can be visualized same as this, right? Here you are getting, in this case, you are getting Mohr circle as a point circle on the positive side of normal stress. Here in this hydrostatic stress, you will get a point circle on the negative side, because all the stresses will be equal and compressive, right? Let's move ahead with this next question. This is the next question they have given you. What they are asking? They are asking you the Mohr circle for the state of stress defined by this, right? So you can clearly see this is your sigma x, this is your tau xy, this is again your sigma y, right? So since sigma x is equals to sigma y, just now we talked about this. When sigma x is equal to sigma y, for biaxial state of stress is equals to 30 megapascal. So when you plot this Mohr circle, it will be giving you like this. So this is sigma x 30 megapascal. This is 30 megapascal, and this is also 30 here. This is also 30. And this is also 30 megapascal. So this is the state of stress. No shear stress is acting, right? You can clearly see this is your reference plane AB, and this is your plane perpendicular to AB, that is AD. So what are the coordinates for plane AB? Coordinates for plane AB will be equal to 30, 0, and coordinates for plane AD is also 30, 0, means in this state of stress, you will get a Mohr circle that will be a point circle. So radius of the Mohr circle will be 0, and the center will be at 30, 0. So you can see here the center of the Mohr circle will be at 30, 0, and the radius will be 0 here. So for this question, your option D is the correct option. This is your correct option for this question. So let's move ahead with this. Okay. So now this question is given. The question says that consider the beam shown in the figure not to the scale on a hinge support at the ends. So my dear, we have completed 3 important chapters. Now we are moving to the last and the 4th important chapter, that is deflection of beams. Okay. So we have completed all the simple stresses and strain. We have completed shear force and bending moment diagram. We have completed with principal stresses and strain. And now we are revising the very important chapter, that is your deflection. See this. The question is saying that consider the beam shown in the figure not to the scale on a hinge support at end A and a roller support at end B. Okay, sir. The beam has a constant flexural rigidity and is subjected to an external moments of magnitude m at 1/3 of the spans as shown in the figure. 1/3 means this length is L, this is L, and this is also L. Which of the following statement is or are true? So first statement says that the support reactions are 0. So let's calculate the support reactions for this beam. Let's calculate the support reaction for this beam. So this is a simply supported beam which is subjected to concentrated moments like this. It's a simply supported beam which is subjected to concentrated moments like this. So moment M is acting here and moment M is also acting here. This is M and this is M. This length is L here and L here. Say, so this vertical reaction here is V1, this vertical reaction here is V2. We know that there is no horizontal forces acting, so horizontal reaction will be 0. So first thing is find out the support reaction. So say this point is A, this point is B. So what you can do is write down summation of moment about A equal to 0. So first you have this anti-clockwise M, then you have clockwise M, and this V2 into 3L. So minus M plus M plus V2 into 3L. So from here, the value of V2 is equal to 0. The value of V2 here is equal to 0. This is V2 and this is equal to 0. Now next is, you can write down summation of vertical forces equal to 0. So when you write down the summation of vertical forces, only V1 and V2 are acting. So I will write down V1 plus V2 is equal to 0. Since V2 is 0, so V1 is also 0. Means statement 1 is absolutely correct. The first option is absolutely correct, that both the support reactions will be equal to 0. So first statement is correct. It's a multiple select question, okay? So first statement is absolutely correct, that the support reactions are 0. Now the next question says that shear force is 0 everywhere. Let's draw the shear force diagram. So when you draw the shear force diagram, check this out. If the point load is acting upwards, at that point you need to move up. How much load is acting here? 0. So how much movement I need to do? 0. So from here to here, there is no load. So shear force will be 0. There is no effect of concentrated moment over the shear force diagram. So means over the entire length, the shear force will be 0. The shear force over the entire length will be equal to 0. So this is your shear force diagram, and in this shear force diagram you can clearly see that over the entire length shear force is 0 everywhere. Now next one is saying bending moment is 0 everywhere. Let's check on this. Draw the bending moment diagram. So first so between A and this point, say this point is C. Between A and C, there is no load acting, so the bending moment will be 0. Then at this point C, you will going to have the hogging moment of M. At this point of C, as you move away from C, you will going to have a hogging moment of M like this. So at this location of C, you need to move down by the amount of M. You need to move here by the amount of M. Then again between C and this point D, there is no load acting, so bending moment is constant. And then again at this point D, you need to move up by the amount of M because of this sagging moment of M. So it is negative here, this is minus M here and minus M here. And then it will be 0. So you can clearly see that the bending moment diagram is not 0 everywhere. It is having some magnitude in this middle 1/3 length. Now last one is deflection is 0 everywhere. My dear, if bending moment is not 0 everywhere, then that bending moment will going to hog the beam over that length. So you can clearly see this. The bending moment is negative here, so beam will going to hog in this portion. Hence, your deflection is not 0 everywhere. So for this question, only option A and option B are the correct answers, right? Remaining two are not correct statements. These are incorrect statements. Let's move to the next question here. Okay, so the question says that here it's a gate 23 question for 1 mark. It's an easy question. The question is saying that when a simply supported elastic beam of span L and flexural rigidity EI, E is the modulus of elasticity and I is the moment of inertia of the section, is loaded with a uniformly distributed load W per unit length, the deflection at the mid span is 5/384 WL raised to the power 4/EI. If the load on 1/2 of the span is now removed, the mid span deflection is. So in simple words, first the beam is like this. This is the initial beam. This beam is subjected to UDL. And the intensity of this UDL is W kilonewton per meter. And due to this UDL, the beam will going to deflect like this, due to which the mid-span deflection, this delta max that you are getting, this delta max or delta naught they have written. Okay, delta naught. This delta naught is 5/384. WL raised to power 4 upon EI. Okay. Now they are asking, if you remove any half of this UDL, what will happen to this vertical deflection? Now observe this. This total effect is the sum of two portion of loadings. This total effect of delta naught is the sum of, check this out, is the sum of these two portions of loading. Means you can see this is the deflection delta 1 and this is the deflection, again this will be delta 1, because both these loads are acting on a length of L by 2. This is W kilonewton per meter and it is acting over a length of L by 2. This is L by 2 and this is W kilonewton per meter. So when you just add these two effects, right, you will going to get this total effect. Sum of these two effect is this total effect. Means you can write down delta 1 plus delta 1 is equal to delta naught. So delta 1 plus delta 1, delta 1 plus delta 1 is equal to delta naught. So from here, what will be the value of delta 1? Delta 1 is equals to delta naught by 2 in simple words. So they are asking, if you remove UDL on any half, what will happen to the deflection? The deflection will going to reduce by half. So you can see it reduces to delta naught by 2. So for this question, your statement A is the absolutely correct statement. Okay. Let's move ahead with this next question. Please try this question. I was looking for this question. It was the question from the topic of shear force and bending moment diagram, but I have kept here. Please try this question. I'll give you just 2 minutes of time. Go for it. Go for it. Try it. Give your answers. Give your answers. Give your answers. Give your answers. Question says that the equation of deformation of derived to be y is equals to x square minus xl. Means under the action of loading, the beam is deforming as per this equation. So y is equals to x square minus xl. Okay. Now they are asking the curvature of the beam at mid-span units. In mid-span is, so curvature, right? So check this out. So slope theta is equals to dy by dx and curvature 1 by r is equal to d theta by dx. The rate of change of slope is termed as curvature. So this is equals to d2y by dx square. Okay. Just do d2y by dx square. So 1 by r is equals to d2 by dx square of y, and y is how much? X square minus 2l minus xl, right? So when you do dy by dx, this will be 2x minus l. So dy by dx, so 1 by r is equals to dy by dx of 2x minus l, and then dy by dx of 2x minus l will be equal to 2. So anywhere over the beam, the curvature is 2. Anywhere over this beam, the curvature is 2. Okay. Let's move ahead. Let's try this question. The question is saying that the planar structure RST shown in the figure is roller supported at S and pin jointed at R. Roller supported at S and pin jointed at R. Members RS and ST have uniform flexural rigidity and S is a rigid joint. Consider only bending, deformation and neglect the effects of self-weight and axial stiffening. When the structure is subjected to the concentrated horizontal load P at end T, the magnitude of rotation at the support R is. So my dear, if you have a simply supported beam like this, right, and this simply supported beam is subjected to a concentrated moment of M at this end. This simply supported beam is subjected to a concentrated moment of M. So first of all, the beam will going to deflect like this. So say this point is A, this point is B. So this theta A here is equal to, theta A is equals to ML upon 6CI. This theta A here is ML upon 6CI, right? Now what they are asking? They are asking that under the loading which is shown to you, under this loading, what will be the rotation at R? So first of all, due to this loading, transfer this P to this point S. The moment you will transfer this load P to S, when you transfer this load P to S, there will be one axial load P acting here, and due to this eccentricity, there will be one moment acting here. The value of that moment will be P into L by 2. So this is the moment, right? Now this situation is similar to this situation. The only difference is the moment is PL by 2. So you can find out the slope at R. This is the slope at R, theta R. This will be theta R. And what will be the value of theta R? Theta R will be equal to PL by 2 into L upon 6CI. So what will be the value of theta R? Theta R will be equal to PL square upon 12VI. This will be the value of theta R, which is equal to PL square upon 12VI, right? So like this, you need to solve for these type of questions. Let's move to the next one. Okay. Can you try this one? Now for trying these type of questions, you should have the standard result, and this is one of the favorite category of questions that are usually asked in the examination. So for that, you should remember all the standard results for the cantilever beam. Let's have a table for standard results for cantilever beam. So standard results of slope and deflection. So you have standard results for slope and deflection like this. So first one, you have a cantilever beam which is subjected to concentrated moment M. The length of the beam is L, flexural rigidity is EI. So this is A and this is your end B. So theta B is equal to ML upon EI. And vertical deflection at B, delta B is ML square upon 2 EI. So for cantilever beam subjected to concentrated moment, theta b and delta b is same, right? I am not taking the signs here. I am just, like what I should say, I am just expecting that you know that if the deflection is happening downwards, that deflection is negative, and if the deflection is happening upwards, that deflection is positive. Similarly, for the cantilever beams, all the slope that will be taking place in the clockwise direction, that slopes will be positive, and anti-clockwise slopes will be negative, right? Next one is the cantilever beam subjected to point load W at free end. So length is L, flexibility is EI. This is A, B. So you have theta B is WL square upon 2 EI, and you have delta B, which is equal to WL cube upon 3 EI. Okay. Next you have the cantilever beam subjected to UDL over its entire length. So this is W kilonewton per meter. Length is L, flexibility is EI. This is A, this is B. So you have theta B is equal to WL cube upon 6 EI, and you have delta B, which is equal to WL raised to the power 4 upon 8 EI. And then you have the last standard result of a cantilever beam subjected to UVL. So length is L, flexibility is EI, this is point A, point B, intensity here is W kilonewton per meter. Okay. So here theta B is equals to WL cube upon 24 EI, and your delta B is equal to WL raised to the power 4 upon 30 EI. So these are the values of slope and deflection for the cantilever beam, standard results. You can have this. Okay, so all these 8 standard results which are written for the cantilever beam, they will going to help you to solve a good quality question, and one such good quality question we will going to see, right? I hope you have this table. Anyways, you will be getting the lecture PDF in the Telegram group. So if you have not joined the Telegram group, the link is given to you in the description box, right? You can join the Telegram group to have this session PDF. So let's see this question, try this question. Where is this question? 1 second. Try this question. Two minutes of time for you, go for it. Go for it, go for it. Go for it. This is one of the, what I should say, a good variety of question, right? Can be asked here. Chalo, see this. The question is saying that a cantilever beam PQ of uniform flexural rigidity EI is subjected to a concentrated moment M at R. Okay. Then you need to find out the vertical deflection at this point Q. Now, sir, how to deal with these type of questions? Check this out. For example, this is the question given to you. And a moment M is acting here, right? So this is point P and this is point Q. This length is L by 2 here and this length is L by 2. Now what can you see from point Q to this point, right? There is no load acting, and since there is no load acting, so there will be no bending moment. So there is no bending for this portion of Q to R, right? From Q to R there will be no bending. Only the bending will be restricted to this point R. Check this out. This is how the beam will going to bend. So till point R there will be bending, and then after R there will be no bending like this. Means whatever will be the slope at R, theta R, the same will be the slope at Q. The same will be the slope at Q. But we are worried about this deflection. This is delta Q. Now check this out. This delta Q can be calculated like this. First of all, this is delta R, and if you draw a dotted line here, so this will be your delta R. What will be this value? So this value is theta R into L by 2. So this is theta R into L by 2. So this is your total deflection at Q. So total deflection at Q is equal to deflection at R plus theta R into L by 2. Okay. For calculating theta R, you have to just consider this portion PR. Consider this as a cantilever beam, and that cantilever beam is subjected to a moment M, right? So what will be the deflection? Deflection will be ML upon EI. So, sorry, ML square upon EI. So M into L will be L by 2 square upon 2 EI. Direct standard result. Then what will be theta R? Theta R will be M into L by 2. M into L by 2 upon EI. You have to consider only L by 2, this portion of the cantilever, right? So M into L by 2 upon EI into L by 2. Just calculate this. So this is equal to M L square upon 4 to 8 EI plus ML square upon 4 EI. So this will be, I think, 3 by 8 ML square upon EI. Just check this. Yeah. Just check this. Are you getting the same answer here? So ML square upon 2 EI plus ML upon EI into L by 2, right? So you can solve it like this. This is your deflection at point Q. Let's take one more question from this segment. For example, if a beam is given to you like this, A cantilever beam is given, and this cantilever beam is subjected to a point load. It is subjected to UDL like this. And it is subjected to a concentrated moment like this. So concentrated moment is 150 kilonewton meter. Point load is 50 kilonewton. This is say 25 kilonewton per meter, and the length of the beam is 5 meter. Flexurality of the beam is EI. Okay. For this beam, you need to find out the slope and deflection at this free end. So these type of questions will be solved by the principle of superposition, right? These type of questions will be solved by the principle of superposition. What you need to do is, you have to consider one load at a time. For example, this is one cantilever beam, one load at a time, and you have to take the sum of the effects, right? One load at a time. So 3 loadings are there. So let me take one load at a time like this. So first is, I will consider this point load here. The value is 50 kilonewton. Second one, I'll take the moment. Value is 150 kilonewton meter. And third one is the UDL acting like this. Now this time, when you are writing the effect, you have to take care of the signs also, right? So this is 25 kilonewton meter, 25 kilonewton per meter, and the length everywhere is 5 meter. This is termed as the principle of superposition, where you take the combined effect of all the loads acting over the beam, right? Chalo, first of all, due to this point load, there will be downward deflection of the beam like this. So this is delta 1, and the slope here will be theta 1. So first of all, what will be the value of theta 1? Theta 1 is clockwise, and clockwise value will be WL square upon 2 EI. So 50 into 5 square upon 2 EI. Please calculate this. WL square upon 2 EI. That will be the slope at due to point load. So this will be 50 into 5 square divided by 2 EI. So this will be 625 by EI. Next, delta 1 will be minus WL cube upon 3 EI. So WL cube is 5 cube upon 3 EI. Please calculate this. Please tell me the value of this delta 1. Please tell me the value of this delta 1. Calculate this. So 50 into 5 cube by 3 EI. So this is minus 2083.33. by EI. Okay. Now next one is this for concentrated moment. For this concentrated moment, again the beam will going to deflect like this, and this deflection will have delta 2 here, and the slope due to this concentrated moment here will be theta 2. So first, what will be the value of theta 2? Since theta 2 is in the clockwise direction, so that slope will be taken as positive. Value of that theta 2 will be ml upon EI. So m is 150, L is 5 upon EI. So 150 into 5 will be 750 upon EI. Theta 2 is 750 upon EI. Now next is delta 2. Delta 2 is minus ml square upon 2 EI. So minus 150 into 5 square upon 2 EI. Please calculate this. So this will be 150 into 25 divided by 2. So this is minus 1875. This will be minus 1875 upon EI. Now coming to this last portion, you have to keep a check. This UDL is acting upwards. So this beam will going to deflect like this, right? So this is delta 2 here. And this will be theta 2. And this time theta 2 will be negative because theta 2 is happening in the anti-clockwise direction. So the value of this theta 2 will be minus WL cube upon 3 EI, 6 EI, sorry. So W is 25, L cube is 5 cube upon 6 EI. Please calculate the value of theta 2. So, sorry, this will be theta 3, not 2. This will be delta 3 and theta 3. And this will be theta 3 here. This is minus 25 into 5 cube. So 25 into 5 cube divided by 6 CI. So this will be 520.83. So theta 3 is minus 520.83 upon EI. Next is you calculate delta 3. So delta 3 is positive this time, right, upwards. So I will write down WL raised to the power 4 upon 8 EI. So W is 25, L raised to the power 4. So 5 raised to the power 4 upon 8 EI. Calculate this. So this will be 25 by 8. So this is plus 1953. .125 upon EI. So you have calculated theta 1, theta 2, theta 3. You have calculated delta 1, delta 2, delta 3. Now the combined effect of all these loads will be the net slope and deflection at the free end. So net slope and deflection at the free end. So slope and deflection at the free end is so slope at free end is theta 1 plus theta 2 plus theta 3. Please take care of the signs. Don't only consider the magnitude. So theta 1 is how much? Theta 1 is 625 upon EI. This is 625 upon EI. Theta 2 is how much? Theta 2 is 750 upon EI plus 750 upon EI. And then you have theta 3. And theta 3 is minus 520.83 upon EI. Minus 520.83 upon EI, right? Please take the sum. So 625 plus 750 minus 520.83. So this is 854.17. So total slope is 854.17 upon EI. This is the total slope at your free end. Similarly, you can calculate total deflection at free end. So total deflection delta at free end is equal to delta 1 plus delta 2 plus delta 3. So delta 1 is how much? Delta 1 is minus 2083.33 minus 2083.33 by EI. And what is the value of delta 2? Delta 2 is minus 1875 upon EI. Minus 1875 upon EI. And what is the value of delta 3 here? Delta 3 is plus 1953.125 plus 1953.125 upon EI. Just take the sum. So minus 2083.33 minus 1875 plus 1953.125. So this is minus 2005.205. Delta is minus 2005.2 upon EI. This is the final deflection of your free end, right? So by this principle of superposition also you can expect a question in the examination from this principle of superposition, right? So like this, if you have a slope deflection question, especially from the cantilever beams, there are high chances that they can ask you a direct question, okay? Because if they will ask you the question from the simply supported beam, it will require some long time, okay? But for cantilever beam, the solution can be done quickly. So this is all what I have to offer for this section. Before going from this section, before closing this section, my dear, I just like to make few announcements here. The first is related to our test series. We are providing you this test series at a discounted price of 40%, and along with that we are also providing you with the GATE question bank of maths aptitude and your technical subjects. We at IMS GATE Academy, we offer you 4 different types of program in which 800 hours of live teaching is provided along with doubt solving and interaction. We provide you with theory and exercise book containing 4000 practice questions, well versed in level 1, level 2 and level 3, so that even you have an idea on which level is your preparation is. We provide you with the 33 years of GATE question bank in which we have provided you with a detailed solution, alternate solution, key points and chapter overview. We provide you with 12 personalized one-to-one mentoring sessions along with India's largest test series containing 130 plus tests. If you want to know more about our courses, you can book a free counseling session for which the link is provided to you in the description box. Moving ahead with this, we have this something called as zero gate free program, GATE zero fee program. So this was one session. As while launching this particular series, we told you that some of the sessions will be happening on YouTube, but majority of the sessions will be happening on our IMS 3.0 platform. So if you want to watch the remaining sessions, you can just enroll yourself into GATE zero fee program. Nothing will be charged, and this is the content that you will be getting for free. Apart from that, whatever revision sessions will be happening, that you can watch free of cost. So again, for this program, the link is provided to you in the description box. You can join, right? My dear, that was a fantastic session. I hope that this session was helpful for you. I tried to include the 4 important topics of strength of material which are having the highest chances of getting asked in the examination. First one is simple stresses and strains. Second one is the shear force and the bending moment diagram. Third one is the principal stresses and strain. And fourth one is the deflection of beams. Always remember the standard results. And if you are expecting a question in the examination from slope and deflection, it will be from the direct results or the standard results of slope and deflection, right? So try to remember all the things that we have seen for today's session. In case if you want to join and contact us, again, for that the link is provided to you in the description box for the counseling session. For our enrolled students, if you have any doubt, you have my WhatsApp or Telegram, you can just text me there. So thank you so much. I wish you all the best for the upcoming GATE 25 examination. For the enrolled students and the other students who want to watch our further revision sessions, that will be conducted in IMS 3.0 platform. So you can join the zero gate fee program for getting the access for that IMS 3.0 program. Okay. So thank you so much. Have a great night ahead. Take care.